jacket. Okay, so we're gonna do. Shoot, I may have lost a piece of paper. A couple of things today. Whatever, things out. So we're going to talk about the exam and back. We're going to talk about what I would call like useful operations or like advanced topics. Some of you will have actually already used some of these. And then we're going to go into the introduction to MIPS, which is a type of RISC architecture. So we're going to talk about microprocessor architectures. I will have out the exam like halfway through. We'll take a nice mental break from that. Until we get to that point, we'll probably need to turn on the smart light so we can actually see. Sorry, my brain's all over the place today, so if I'm a little scatterbrained, I apologize. So the first thing that we're going to talk about is an idea called generics. Now, I've talked about writing code for reuse, right? So like, take a SPI interface. If you've got a job that is working for an instrumentation company, you might design a SPI interface a dozen times a year. Now, ideally, you wouldn't sit down and rewrite the code, even though that would be easy. You would want to write code that made it easy to reuse. Now, SPI has a lot of variations. In fact, you'll notice our device even is described as a SPI-like. Right. And it's because it'll take SPI and like most of it, but I can change this. Now, the obvious changes is we use mode 1, right? But there's modes 1, 2, 0, 2, 3. So there's 4 different modes. And you could have any number of combination of bits, right? You might have some amount of command and data packets varying from 4 command to 4 data or 12 command to 2 kilobits of data, right? So we want to write code that we can then reuse regardless of all these little things that they change on us for SPI. We do that using something called generics, where during the instantiation or the creation of a component, we can pass it parameters that are then used inside of the instance. So each instance can have its own parameter. Okay, so let's say I do that. I'm just going to first walk through the example on page 413. I'm going to skip some stuff because there's tons of code. But maybe I'll find one that works. There we go. Okay. So, the example that they want to start off with, which is just fine, is going to be RAM, it looks like. Nope. Not the other one. Entity of NAND2. Okay. It wants to pull the generics of T-rise, T-fall, of type time. I'm going to end it there. They also use I'm just going to skip over that for this point because I can make the point without it. Port A, B, ends, bits, C, out, bit. So, in this case, let's say I was building up a NAND gate, but its rise and fall times changed based on the number of devices that I was attaching it to, right? Because a gate can only drive so much capacitance and meet timing. So if I can't connect 100 devices to the output of this one NAND gate, it's going to slow it down. So in order to simulate correctly, I'm going to say that it has a rise time. It changes based on the number of devices. Now we know that this after it doesn't synthesize, but we want to simulate things correctly. So we create the generic statement. So just like port, right before it, we declare what generics we're interested in and what their types are. This type time, we know it's not going to synthesize. Then inside of here, I have this T-rise. That is not going to come from a declaration in here like a constant like we've learned in the past. It actually in when we create, in this case, the component. So when we go up and build the test of this, when we create the component of this, we would just write, we'll take a moment and explain. So this C, we have a rise time and a fall time that we're interested in, right? This is just creating a situation of, we use the rise when it's already 1, and then we use the fall when it's 0. Is that correct? I think they have that backwards, don't they? Yeah. Yeah, I think the book might have a typo in that one. So when 0 perhaps, right? To differentiate the rise. So it's just going to make different decisions based on whether it's 0 or 1, and use the past T-rise and T-fall. We pass it to there by saying something like component, okay. All right, so we create the component like we normally would, except we add in the generics and let it know that does exist a T-rise and a T-fall. Now, in the component declaration, this is just saying if I don't otherwise say, let's default to 3 nanoseconds. So if in this instance, right, so here's the component, here's the instance, right, this comes after the begin. Inside of the instance, I could leave off the generic map, and it would assume T-rise is 3 nanoseconds. Or inside of the instance, I can say, in this case, T-rise is 2 nanoseconds and T-fall is 1 nanosecond. I could then go on and say something like, hey, there's also U2. And this one has 4 nanoseconds and 2 nanoseconds. Right? So every instance that I create is giving me the opportunity to change these parameters. So let's build something a little closer to home for us. Let's think about this with a memory, right? So we can do the exact same thing. We're going to say I have an entity. We're going to call it RAM. It's going to be it's going to have the generics. And then I want to have variable data widths. And I can initialize it here, in fact, if I would like to, which is an integer with a default value of 64 and an address width, which is an integer default value of 12. Ports, blah, blah, blah. And let's stop there for a second. Okay, so we use the IP core, right, when we created our ROM and our RAM. ROM for SPI, RAM for I2C. But if we want to create one of our own, isn't using an IP core, we can assume that we're going to create lots of these, right? We'll use these all the time, various things. We want to have varying data widths, meaning how many bits are available at one time, and varying depth, which is how big is it really, right? So it could be, in this case, it would be a 64 by 2 to the 12, right? So the address width is how many bits of addresses do we have? You can then go ahead and calculate everything else you need with just these two. So this is creating the width, this is the depth. And you've seen something like this when we created the ROM, right? Where we're wanting to use 100,000 locations, 100,000 addresses. The ROM didn't create it with 100,000 addresses. It created it with 2 to the 17 addresses, which is like 131,072 exact, right? So the issue that you might have run into in your SPI is if you're trying to only go to 100,000 and you spill over to this address 10001, nothing's there. So you initialize the values for the first 100,000 addresses. The next one is just 0. So this instantiation would avoid that, and you don't have a way of creating it with only 100,000. You have to create it with values of 2. So here, for your case, you would just say 17. So anyways, we've created a RAM. Let's just say I've declared the component. I won't draw the declaration. Let's create the instance of it. RAM1 is a RAM, and it has the generic map of data width is equal to, in your case, it was what, 12? And your address width is equal to, these are these zeros, 17. Right, now I've created that generic map. When this ROM gets instantiated, it will make my RAM the size I want it to. So that's generics. That's all they really are. It's a way of passing parameters to your components upon instantiation. So each instance can be different. You can see how this could build up and do something really useful, like an n-bit adder, for example. Right? Well, let's take it to the next step. What if we wanted to, right? We remember when you guys made, I hope you remember, in 2700, you guys would have made, what, 4-bit or 8-bit or 16-bit adders, right? And they're ripple adders. And when we make a ripple adder, we're going to erase this. When we make a ripple adder, we just start by creating one full adder, right? And chaining them together. So we'd say something like, all right, this is my full adder. It has inputs, it's going to add A and B. It reports A and B. And then it's going to have a carry in, carry out, and a sum. Right? And when I want to make this a 2-bit adder, I then say, okay, well, this is A at 0, B at 0. Well, that's not quite right, is it? Let's say it's going to be a 4-bit adder. 3. Nope, it's at 0. Just getting ahead of myself. I take another full adder. It has A's and B's. C out, C in, or A, or B, blah, blah. Right? So what we would do now with our current set of knowledge is we would create one component. We would then create multiple instances. We go an instance, another instance, another instance. And that's good for like 4 bits, right? After that, it starts to get really tedious. So at that point, maybe we'll build a component called a 4-bit adder, and then we'll just start stitching 4-bit adders together. And then if we really need to do, say, 128-bit adder, then maybe we'll be like, all right, let's make a 16-bit adder and cascade that until we have it, right? That sounds obnoxious, especially if I start getting to large numbers. And let's move on from an adder and say we have like a shifter, right? So we're trying to shift something in and then shift something out. So it's just a queue to transmit data out over USB or something, right? Well, that could be 2 kilobits, right? You have 2,000 modules. That would be awful to write. Well, nice little technology that a couple of students have stumbled across called generate. So what generate does, incredibly helpful, is it generates, using a loop, instances of the component for us. So let's build up a nice, simple example of those. So generate, I'm just going to say, I'll start with the generate statement, I think, might be the easiest. So let's assume that I have a full adder, right? And I want to use multiple instances of it. Then I can just say something like this. I want to build a 4-bit adder using these full adders that I've already made. For I in 0, 2, 3. Now we've done loops before, and at this point normally I would write in 0 to 3 loop. This is the only difference. I say generate. And then all I have to do, begin, okay. So in our instantiation, I say full on for I in 0 to 3, generate instead of loop. I then say FA X. I pull in the full adder, assume we have that component. And I throw its port map using the loop variable. So I'm going to take A at I, B at I, C at I, C at I plus 1, and S at I. So with the exception of the carries, these are just going to be ports that I've created for this overall entity. I would need to create a C signal. Stand logic vector or right? Because it needs to have more than one. So the carry in we're going to initialize to 0 unless we want to do something with it. Then every other one is going to take whatever the carry is and stitch them together for us. So instead of copying and pasting and then updating all of these, this generate for us is going to create 0, 2, 3 full letters that are connected together one by one for us. Now, we could actually go back and combine this with the generic, and instead of using 3, let's pass it n. Now, we probably need to do a type conversion between that and that, but that's not really an issue, right? And so now we can generate n-bit adders with only a couple of lines of code. So when we start mixing parameters and generates, we can start using these ideas, and they're very helpful in space-constrained systems especially. Because we can, instead of writing something like, oh, this is going to be big enough to handle whatever I need, instead we write the code that we can just pass in parameters and we'll only make subsystems that are as large as we need them. So if you're trying to optimize size and versatility together, generate and generics are your friends. Now, something that I'm not going to go into depth on because it's kind of a niche application, but I do want to point out on page 420, it actually goes over an example of how you can use VHDL to call files. You can actually load files and use them to initialize values inside of your VHDL. Now we've done this using the IP core for the ROM, right? The code that they use is very similar to what is presented on page 420, where we have an external file and we need to load those values into our system because we need to start from somewhere, right? And that will show you how to do that if you ever come across it, right? If you say, keep this book and you go on to become a professional and you run into a situation that the IP core doesn't quite address, you can kind of build your own. But I'm not going to cover that because it's kind of straightforward, actually. So let's go ahead and take a short breather. And I will pass out the exams. Okay, see. No, like first beginning of the exam. Good, because I would have lost something. Okay, so I'll just start marching through this. I posted some statistics to an announcement that kind of talked about it. Once again, there's no real difference between the day and the night class. In both classes, about half the people took it online and half the people took it in person. The difference between the online and in person was almost nothing. The online people actually did a little bit worse, and by a little bit I mean like 2% on average, so very, very low. Than those that took it in person. It looks like a wonderful bell curve It's great. I did curve it up plus 10. I may actually end up adding a couple more to that because there was a commonly missed question, but it wasn't your guys' fault. It's because the book was wrong. I'll get to that. It's number 8 and 9. Okay, so number 1, you guys got mostly correct. The most commonly missed one on this one was the fast carry adder was listed as sequential instead it is combinational. You can tell that if you just flip to the page where it talks about the fast carry, or sorry, not the fast carry adder, the array multiplier is the most visible. The array multiplier is all combinational. So every other type of multiplier has sequential logic. The array one is combinational, which would make it fast and huge, right? Number 2, the only trick on that one is some people listed reset or clock. They don't do anything for you because it's combinational. So we don't need to reset it or clock it. The true false were mostly correct. With 3, people just, I think, flipped in their heads which one was which. 3 is the principal difference between a PLA and a PAL is that the OR array for the PAL is programmable. Holy crap, did I do this one wrong? Whereas the OR array of the PLA is fixed. Did I screw that one up? Sometimes it's helpful to get called out because I get, it is a 50-50. We'll find out really quick. It's not. Yeah, I could see. 1140. I think you might be right, and I think I may have screwed this one up. It's funny how, like, I think I know what the question is that I wrote, and then I get it wrong. Because this would be really funny if I screwed this up, because that means that I didn't actually need to curve the exam at all. What did I say that was wrong? And I now would see this now. Okay, so I'm correct. It is false. Good. Don't worry, if I screwed up, then I wasn't gonna, I would just give everybody points back, but if I got it right, I'm happy. I hate true false questions sometimes because they get confusing. The other ones were almost all right for everyone. There were a few people that, oh, sorry. Oh, I see where I skipped. Yes, it's just the reading of it is tricky. Number 7, I think everybody got right, so congratulations. Okay, 8 and 9. Now this is not your guys' fault because the book has, so the answers as far as I would have done them, like if I'm looking at it, is 4 and 10 or 12. But the book has a table apparently that I missed, that is wrong as far as I can tell, because it lists specifically on the 4-bit ripple carry, it listed as 8, which I don't know what they were doing, because the equation, there's like literally just an equation where you just say it is 2 plus 2 times the number of bits, and then if you worry about the carry out as well, it gets another 2 gates. Because each of the adders has 3 gates to generate the carry out. So it's 3 times the number of bits. You can remove 2 of the gates at the end because if you don't care about that last carry out. So 10 or 12 is correct. I actually don't know what logic they use to generate their 8. As far as the fast carry, again, I don't know what they use. It's not that hard to make a 4-bit with only 4 gate delays. In fact, the most straightforward implementation is 4 gate delays. But the table says 5 or 6, I think is what the table says. So 8 and 9, tons of people, not everybody, some people like actually figure out the circuit of like the adder, like, okay, that's 12. But I can't blame you guys because the book said something else. Number 10, lots of people missed, about half the class, I think. And I think it all came down to not reading it. Like, you saw something and you thought you knew what the answer was, or the common misunderstanding of it's an integer, right? The question is, how many bits will be allocated for the following signal? And it's an integer from -1 to 13. The important one on this is to understand that when you declare an integer, your digital logic will create it as a 2's complement. It can't have a no bits answer. That's the most wrong one that I saw. It's no bits. Well, no, it does have bits. So numbers, it's universally this 0.2's complement how it's stored. So then it throws 1 bit as the sign, and then it needs 4 bits in order to be able to count up to 16. So it's 5 bits. We'll see how we create that. Number 11, the simplest method for multiplying by 2 is just to shift it. Some people wrote shift right, so I wrote shift left as the answer. If you just left it as shift, it's still correct, because technically shifting right on a little endian would be correct. I didn't give you whether it was big endian or little endian. So as long as you said shift, you should get points for it. Number 12, the main issue was chip select never goes high. Now, load could be viewed as a problem if you wrote the code as if rising edge upload. In general, you shouldn't do that, so you have partial credit for this. You shouldn't use rising edges on non-clock signals. So if load is still 1, it'll just keep going again. The busy is an output, so we don't really care about what busy is doing, right? The busy can simulate correctly, but it won't cause any issues in the system. Again, partial credit if that's what you did, I believe, but chip select is that it will fail because of that. Number 13, this one was a nightmare to grade. The way that I did it is I essentially went through and made sure that it was microcode compatible first off. So that's page 287, where it just lists 2 bullet points. Eliminate all conditional outputs by transferring to the core machine, and then make sure you test only 1 input in each state. Now, a common mistake of doing that was right? So from this one state, I could end up in 3 different states. If that's true, I'm no longer microcode compatible. Now if, because one of, right, because I used some don't cares in here, if one of them these could be combined, and it looked more like this, right? This would technically still be okay. Not quite right, but it would ultimately mean that these is really only one decision. And the other one is you had to draw boxes, right? Most of the time that was just people rushed over it, I think. Use of the output gates, right, again, not allowed because it's not microcode compatible. Question? the way I would recommend doing it is I create a substate, yeah. So if this is S0, I would have one that is like S0A, and then it would make a new decision. And then I could make this box and that box. So that's why I said you may need to add additional states, which you do. I don't remember. I remember grading you. I didn't know that was it because I don't think that's incorrect. The C is good there, but it needs a state A. It's not a state B. And that should be that's probably easier, but I accidentally did that. Right? Yeah. So I did mark you down. I did mark you down some. Yeah. Because I understand, like you are almost there, but it's still not quite correct. Yeah. Yes. Yeah. Yeah. So I ended up with 9 states. I think most people that got it correct did it in 10. I ended up not marking down for that, I don't think. Because 9 or 10, either one is reasonable. Yeah. 10 is still a reasonable amount. It's just that one of the states can be combined. And I decided not to grade on that because it was fine. Number 14, you guys killed it, to be honest. The most common mistake was missing that for F2, you can circle a block of 8. And a couple people just colored the wrong bubbles or didn't label F1 and F2. But overall, you guys did really well in this one. So on the next one, 15, the code, and this is just the thing that I've been harping on. And now I can clarify something, because the correct wrong answer for this one, the thing that's wrong, is I'm initializing a signal, right? The most wrong, so some of you called out the for loop, which is good awareness, but the most wrong thing is still the signal, blah, 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 is equal to a number, right? So this causes issues sometimes, but it is the most likely one to cause a problem. Now, I say don't ever rely on this because you don't know what's going to happen. So I've done some tests with our FPGAs, and most of the time this works on our FPGAs, but it actually doesn't work all of the time. And the difference seems to be in our FPGAs, if you ever change this value inside of a loop, it doesn't work. But if you don't change it, it'll just assume you enter a constant and then create it as a constant work just fine. The time that I know, the time that I know that it never works is in VLSI. When you're writing code to make an ASIC, this will never work. If you call it a constant, it's fine, but saying it's a signal, it will get confused and be disastrous. So that's why I have to add the line, assuming you don't know the target technology. Because if you do know the target technology, you may be like, oh, this is fine. But if you don't know, this is problematic. The way I would do it is, depending, is if I'm in idle, then I would say this is signal S, right? Or if it's not a state machine, I would just say if reset, right? I would create some situation where it goes to that reliable, yeah. It would just be fine, yeah. Yeah, and if it doesn't ever change, the synthesis actually does a good job of assuming it's a constant, doing that for you. But I have find situations, and it's not even every time that I change it that it breaks. It's just sometimes when I do that, it does my additionals. So So I still don't yet understand what this FPGA is doing to try and make this work versus not. Okay, the last one you guys did, again, really well. So in the simplest form, there were 3 things wrong with each of them, but there were ways that you could interpret them as multiples, or you may have corrected to do it more complicated than I would have. So I left 5 lines. Only one person went over on the 5-line thing. But the errors in the test bench on line 24 was missing a 0. So it just had the wrong number of zeros in the initialization. I misnamed busy in the port, so BSY instead of BUSY. And then this one was the most missed one, is the status lights, right? So I said you need to correct the issues in the test bench, including those that prevent it from running, and issues causing X or U outputs. So as long as you did something with that status lights, I was okay with it. The correct way to do it is inside of the module, it had a port called status, but in the port map, I didn't list it. So all you would have to do is add that line that says status and then map it to status lights and correct the number of bits. That would have been the easiest way of fixing that. There are other things that you could have done, just use status, but that was the main one. That may have been the trickiest one to catch, because not everybody can yet realize that I don't need to call out all of my ports in an explicit port map. I can just leave them off, and it is okay with that, as long as there are outputs. The spy master errors, so when I initialized it, I said it has the range of 0 to 15, but then I later wrote bit count is equal to 16, and that doesn't throw an error anywhere. Initially, it doesn't have any of this squiggly lines, but it will cause an issue once you run the simulation saying out of bounds. The other one is the state type. I had TX instead of TX1. So you could either change all of the TX1s to TX or just change the state declarations to TX1. And then I used sdata0, which is an output on the right side of the declaration, which you can't do. A couple ways to fix that. You could have changed it to an in-out for a buffer, or you could have just declared it to the same signal that sdata1 was. There are a couple ways to fix that one. And that was the exam. I'm going to look at, because of the represents the curve I just like having that method that change like this time. how you use them. It stands for reduced instruction set. The idea being that we want to have a fairly few number of instructions and still be able to accomplish everything. So like one other set is CISC, C-I-S-C, which is like complex, ISC, whatever, right? It has 80 instruction sets, which is actually technically fewer than the MIPS, but each of those 80 has 12 different ways that you can use it or something insane. So you end up with thousands and thousands of potential instructions, which ends up being really difficult to decode. So we'll talk about MIPS and how it takes instructions and does stuff with it. And you guys have a little bit of a clue from 2700 where you built the a little bit of microprocessor architecture using the ALU, right? And I understand that may have not been the best education that we received for some of you as it fell apart, but it's still relevant. So some of the conditions that we have for what does it mean to be MIPS, right? So MIPS makes all instructions the same length. Now this has the benefit of easy to decode, but the penalty of, well, sometimes instructions are really simple. So if it's a 32-bit instruction that are universal, we're suddenly wasting some bits potentially. They decided that it's acceptable to keep it simple. They actually had thought about calling it CISC, S-I-S-C, instead of RISC. They didn't because SISC and CISC doesn't pronounce differently. So they wanted to differentiate it. So the other big one is they keep the addressing modes simple. So they basically usually pick one type of addressing mode and stick to it. So the easiest one to use is direct addressing. I give an address, I get an address, right? The other one is immediate addressing. Immediate addressing just says whatever is next. So those two in a combination is really common. So you can say either give me this specific address or give me the immediate address. And that's what your 2700 project would have been. Those are the two types it used, is load from somewhere or give me the next one, right? But you can go into other ones. You can do like base plus offset. So you have an assumption and then you just define the offset. You have like indirect addressing and a bunch of other ones, but we'll not worry too much about those. The next one is it uses a large number of registers and has a few number of processes that will access memory. So in some computing architectures, you'll be just pulling stuff in and out of memory all the time, but memory is slow compared to registers. So it uses lots of registers and only writes to memory when it has to. It also avoids what they like to call in this book implied operands or side effects. Now what that means is I love implied operands personally when I'm designing FPGA logic. The most prolific example of these is what we call flags. And I've talked about using flags in the I2C to dictate if a condition is true. RISC hates flags. It just wants to use just the basic commands because flags can get out of control really quickly if you use them everywhere. I love flags though. So my design philosophy is at odds with RISC. Okay, so inside of RISC, they have what we call instruction set architectures or ISAs. We are going to be talking about MIPS. MIPS comes from like a specific company that existed in the 80s or something, might still be around. But doesn't really matter. MIPS itself is a little bit outdated inside of the RISC architecture, but as I said, it still exists. So what it's going to do is essentially it's going to take the shape of a 3-address format for almost all operations. And so if you think back to your ALU, right, you have an opcode which tells it what to do and then takes inputs and then throws it in the output, right? So if I'm writing the add and commit the two things I need to know, well, three things. What am I adding in A and B, and where is it saving? So I would just write, oh, and the registers inside of MIPS architecture, they label as dollar signs. So it'd be like $0. So if I want to add something, I say add, and what this would do, it would add 3 and 4 and store it into 5. Each of these registers is probably, for most MIPS, going to be 32 bits. They are not variable sized registers. They're fixed at some number of bits, probably 32. So you can do the same thing. You could say something like sub those, and it'll take that action, right? And so now we're seeing where that ALU that you guys designed in 2700 matters, right? Because we're really just passing an operation to an ALU that's taking 2 inputs and storing it somewhere. In 2700, we only took one address, right? Because we either kept the memory in the accumulator and brought it back. I realize you guys might not actually remember that because for some of you it might have been years ago. It's not that far different. Right. So this is the arithmetic logic unit. And the one you guys designed, it only takes B out of memory and then adds an E. It can add to the accumulator or not. But if it wanted to do 2 addresses, it would have to send the load command, which would take B and sort and accumulate, and then the add command with the new address, right? This one does not have that feedback. And it would just tie up these 2 various registers and store it in a different register in the MIPS. Things like add, subtract, or add or subtract, say, has, let's bring these down, what we would call an add immediate. So you'll see this I a lot. What that does is instead of taking 2 registers, it would take the output, 1 input, and then what am I adding to it? So I just say add 100. Take 3, add 100 to it, and store it in 5. You can multiply, divide, etc. The issue is, let's say we had 8 bits in 3 and 4. I multiply 2 8 bits together, I get 16 bits of output, right? So that can cause us an issue. So it creates these kind of dummy registers called high and low, and it has like an artificial 64-bit register in order to do that multiplication, and then you can store them however you need. Other operations, you can, well, you can do the logicals. You can do AND or XOR, etc. Actually, I'm not sure if MIPS has XOR. I think it might have only AND words, which makes it really annoying. And it would just be the same. You just say and right with dollar signs. It would do the same thing. And B and C stored in A. Or you can AND it with immediate, where instead of register C, you put some constant K. Now, all of these are storing these in registers, not in memory. If I want to store something in memory, I have to explicitly call out, let's save or load. So you could say something like LW, the register, so what this is doing, this is an L, by the way, LW. It's computing the memory address as the sum of the value in register 4 at the offset of 100. So it takes a number in 4 as the address, and it gives it 100 as an offset. So if the register contains 4000 as a number, the thing that would save into memory would be 4100. The 5 into the memory address. So this is loading from memory, sorry. Yes. So taking what is in memory at address 4100 and puts it into register number 5. Store into memory is S. And that's taking the contents of register 6 and storing it into memory at the address of whatever is in 8, offset by 100. So if 8 had the address 6000, then we would store it to memory at 6100. Okay, so now we have to do the next annoying thing. I don't even know if you guys got to it in your 2700 lab, which is where we interrupt the process counter, right? So we have this idea of the PC, the process counter, that just tells the program, the controller, where it's at. But sometimes we don't want to take just the next instruction and then save it back into memory where we were, right? We may want to jump ahead, save something, and then come back and continue. We may want to loop through something, right? To do that, we use what they call control transfer instructions. And those would look something like B, and what we're going to do here is we're going to compare the contents at 5 and 4 and then branch to the process controller. This is stupid. I hate this one. At a location of wherever we are, plus 4 plus 4 times 25. Now, the 4s come from because they're converting to byte instructions, which is obnoxious that they use the format that they do. But be aware. So the way they'll write this in the book, they just skip to this. But that 100 is coming from the 4 times the input. So, yeah, sorry. So it has branch on equal. So if they're equal, do this. They also have branch on not equal, which is B and E. Yeah. Oh, this is basically saying next. Where we are plus go to next plus some amount. Well, that 5 is an input. Yeah, so we say BQ operand 1, operand 2, jump 2. Essentially. This is 436 right now. jump ahead that many times. Yes, because it's not 4 per. Get another question, JC. Okay. You can also set values based on these operational comparisons and reset based right set to 0, set to blah blah blah. So these are BEQ and BNE are really like the fundamental for loop stuffing stuff. We may also just want to jump, where we would just say something like, I really hate these ones. Jump to this process controller output. Where again, when it actually looks at this, it's going to be 4 times the address. We can also jump to a specific register. A few other things we can do. So we can then start talking about code, right? How do we actually do something with these operations? Fortunately for us, we're learning Python and we're not writing in MIPS because that would be miserable. But I don't know if you guys write this program doesn't have MIPS as our standard language, because that would be awful. So let's say we want to run a loop. And that loop is going to have 100 elements, and it's going to loop through X and Y, where it's going to just take this operation. Right, where we're going to iterate through and start updating Y by adding an X value to it. We're going to loop through 100 of these. And it says to assume that X and Y start at 4,000 and 8,000 for their starting locations. So then we're going to go ahead and start writing this loop. We're going to start writing typos, I guess. Okay, so first off, we're going to take ands, and we're going to and the contents of 3 and 2 with zeros. What that does for us is just set them to 0, right? Because if we and something with 0, we always get 0. So now we're storing zeros to make sure that they're clear. It is then adding 400, so add immediate 400 into 2. Right? So 0 plus 400 stored in 2. That gives us, this is going to save our loop bound. Then we're going to, remember, we always do it stupid multiples of 4 right now? Yeah. Okay. Now we're going to load 4,000 and 8,000 into registers 15 and 14, like memory locations, right? And so we're loading up our X's and Y's and storing them to registers 14 and 15. Then we want to start adding them together, right? Because that's what operation was. So we just say add okay. So now we're going to do our loop operations where we're adding X and Y, storing it in 24 register. And then we're storing register 24 back into memory. Then we're going to take, right, number 3 up here, and we're going to start incrementing our loop counter. So this is our loop counter, keeping track. We started at 0, and now we're adding 4 to it over and over and over and over again. Because of the stupid byte addressing, right? But when do we stop? Because we need to make sure we go back. So I'll use that BNE that we just mentioned. Oh, I forgot one stupid. So now we're just gonna look for 3 and 2, right? And if they're not equal, we'll jump back to where we labeled them. Yeah. Well, no, 2 is 400. So we reset at 0 and then store 400. Okay, so 3 starts at 0. 2 starts at 400. Then here, 3, it's add immediate with 4. By 4 up to 400. Yeah. What's that? It is. But we have to do the talk at low levels to stuff, so this is like what your compiler is doing behind the scenes on a microprocessor. Okay, so the way that they format these commands is a 32-bit command where the first 6 bits are your opcode. Now they have this, the opcode is universally true. They have only, fortunately for us, 3 different ways of formatting commands, depending on what they are. So those formats are R, I, and J formats. So for R, this is your arithmetic functions, add, subtract, multiply, etc. So it's going to have the opcode followed by 2 5-bit addresses, which are your inputs, followed by a 5-bit address, which is your output. And then you're going to have 5 bits that are generally unused, then these are your shift bits. You want to shift by some amount, they're stored in that. So you can shift by up to 32. Then they have 6 bits that are extended function code. These are used because some things are not able to be described at just the initial 6 bits, because there are more than 2 to the 6 operations that can be done, but there are 2 to 6 top level functions, and then there are sub functions there, so that those last 6 bits are reserved for like clarifying what type of operation. So some of these might be like, they might include like jump data. So you have the jump opcode and then how far is contained in those last 6 bits. For the I format, which is load, store, the BEQ and BNE commands, it's just the opcode, 2 inputs, and then just whether we're offset or immediate. So it has tons of overhead compared to what it actually needs. The cost of simplicity in formatting, I guess. The J format is only for jumping, where it's going to have the opcode to say, hey, we're going to jump, and then all the rest of the bits are jump to where. That's all. If you look at this, that is summed up on page 438 in a table you can go back and look at. The detailed description of what they all mean is on 439, but I gave you the essential important overview of that. And then 440 has, well, let's get into this one. This one's going to be awful if you had to read through on your own, so I'll save it. So let's remember that whole thing that I just erased and shouldn't have. And consider, what does this look like in binary according to those instructions? And I'm not going to do a lot. I'm not going to walk through all of these because this would be so tedious and you want to do terrible things to me. So let's look at just the instruction and immediate with the 0, right? So it's going to use, which maybe I should do a different one. Maybe I should add immediate. Yeah, let's change this instruction just a little bit so it's a little bit more interesting. Add immediate. So, I'm going to flip back to this table, and I know that add is in R format. R format, for the first 6 bits, needs the opcode. Well, if we were to go and look up the opcode for add, it would be 0, 0, 1. Then, the next bits are the addresses. Okay, so I need to then store 0, 0, 0, 1, 0 for my address. I repeat that, so this whole thing repeats because we're doing both of them, right? It's 2 into 2. And then for add, the next one is the destination. So, good question. It's 15 to 11. That's interesting. I feel like this is violating its rules. So what it's telling me is the next one is, okay, so this is 31 to 26. This is bits 25 to 21. Bits 20 to 16. 11, 10 down to 6, and 5 down to 0, right? And it's saying that 10 down to 6 on add immediate would be 10 down to 6. What is this in binary or in decimal? One minus 1. Yeah. So 30. Where does the 30 come from? Man. I did the first one and it made sense. And now I did jump this one thinking it'd be better illustrated. And I was like, wow. This is page 441. And I'm on line 3 of the instruction set. This is the opcode for sure. I feel good about that. This is a read address of 2 and a second read address of 2. Right? Because we're adding, wait, no, we're adding 2 and 4,000. Add immediate. Oh my gosh. It's because it's the wrong freaking format. The add immediates are J format or I format. So it is input 1, input 2, and then offset or immediate. So this is saying, this is a command saying it's immediate. And then the rest of these, does this whole thing add up to 4,000? Yeah, 16-bit. Well, there should be 6 and 6, right? Oh, 5 and 6. 11 bits. Okay, good. There we go. Helps if we get in the right format, I guess. So anyways, yeah, that is now your binary for this instruction. And it goes through and provides you with all of the binary for that whole program, which sounds awful and tedious, doesn't it? And so they have tables for all of the commands showing what they would be. And I'm definitely not going to have you memorize them, so just be aware the tables exist. And how to read them, and how to not make the stupid R versus I mistake. So R is for arithmetic, I is for immediate arithmetic, and some jumps. Okay, I'm going to stop there. Why does your guys' class always go so much faster than my lecture? Yes. I don't understand your guys' lecture sometimes because the other one took the full hour and a half to do the first section. And we're at an hour and a half, so. Do I talk really fast at night? Is that the issue? Yeah. Or we might not ask as many questions. I mean, yeah, you guys are half the size of their class, and on average, better students. They do have one student that they might be watching this. They have a couple of students that are really good at asking questions, like really just like curious, want to know every detail. So that does take some time. This is fine. It's not problematic because, like I said, I do want to give you guys additional time to get through the labs, and I will hang around either here or jump back and forth between the lab and the room to help you guys out. So, unless there are any questions on this brain drain of topic.